Dear students, welcome to the 8th session of our chapter 4 Chemical Bonding and Molecular Structure. Today we will discuss about the molecular orbital theory. Molecular orbital theory was developed by F. Fund and R. S. Mulliken in 1932, and the silent features of this theory are: the electrons in a molecule are present in the various molecular orbitals, as the electrons of atoms are present in the various atomic orbitals. The atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. While an electron in an atomic orbital is influenced by one nucleus, in a molecular orbital it will be influenced by more than two nuclei, depending upon the number of atoms in the molecule. Thus, an atomic orbital is monocentric, while a molecular orbital is polycentric because of the number of atoms in a molecule. Then, the next point for the silent feature is: the number of molecular orbitals formed is equal to the number of combining atomic orbitals. When two atomic orbitals combine, two molecular orbitals are formed, and one is known as bonding molecular orbital and the other one is said to be anti-bonding molecular orbital. Bonding molecular orbital has lower energy and hence they are having greater stability compared to the anti-bonding molecular orbital. Just as the electron probability distribution around the nucleus in an atom is given by an atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by a molecular orbital. And these molecular orbitals are like atomic orbitals, like they are filled in accordance with the Aufbau principle, which is obeying the Pauli's exclusion principle and the Hund's rule. The different types of molecular orbitals are there, and for diatomic molecules we can designate it as sigma, pi, delta, etc. And we are learning about the sigma molecular orbitals and pi molecular orbitals. In this nomenclature, the sigma molecular orbitals are symmetrical around the bond axis, while the pi molecular orbitals are not symmetrical. Energy level diagram for molecular orbitals. The 1s or atomic orbital on two atoms form two molecular orbitals, which can be represented or designated as sigma 1s and sigma asterisk 1s. So we can just pronounce it as sigma star 1s. That means when two atomic orbitals combine, we are getting two molecular orbitals. One is bonding molecular orbital and the other one is anti-bonding molecular orbital. And here the bonding molecular orbital is the sigma 1s. Antibonding is represented with sigma star. And one more thing we have to remember, that bonding molecular orbital is having less energy compared to the anti-bonding molecular orbital. That means anti-bonding molecular is having higher energy. So whatever orbital it is, if it is bonding, it is having less energy, and anti-bonding it will be having higher energy. And how this bonding molecular orbital is formed, when we define it, we have to say that it is due to the addition of atomic orbitals, while the anti-bonding molecular orbital is formed by the subtraction of atomic orbitals. So this point we have to keep in mind. And if in the case of 2s or 2p atomic orbitals, that is total 8 atomic orbitals on two atoms are there, then it will give rise to the following 8 molecular orbitals. Which are they? That is, for 2s we will get sigma 2s and sigma star 2s for bonding and anti-bonding. For 2p we are having here p, x, y and z it is there. Subatomic orbitals are there. So for sigma 2p z it will be bonding and sigma star 2pz will be anti-bonding. Same way, when it is the pp sidewise overlap, we know that it is a pi bond formation. So here the bonding will be pi 2 px and antibonding will be pi star 2px, while the other one will be pi 2py and pi star 2py for the antibonding. So like this, we are getting the 8 atomic orbitals. When these atomic orbitals combine, we'll get the molecular orbitals. So these are the 8 molecular orbitals. The increasing order of energies for the various molecular orbitals are 4 for oxygen and fluorine. Like oxygen, fluorine and neon, you can use this increasing order. That is how we are writing the Aufbau principle. Same way 1s, 2s and 2p comes. Here the bonding and antibonding is there. Then again bonding, antibonding and bonding, antibonding. Like this the order goes. So how we can write the order? Sigma 1s less than sigma star 1s less than sigma 2s less than sigma star 2s less than sigma 2pz less than pi 2px equal to pi 2py. This refers that these two are having the equivalent energy. That means these are the degenerate orbitals. Less than pi star 2px less equal to pi star 2py. So again the antibonding will be having a equal energy less than sigma star 2pz. And it has been experimentally proved that the molecules such as boron, carbon, nitrogen, the order is having slight change. That is sigma 1s less than sigma star 1s less than sigma star 2s less than sigma star 2s then less than pi 2px is equal to pi 2py less than sigma 2pz less than pi star 2px equal to pi star 2py less than sigma star 2pz. So what is the change is after sigma star 2s. Here it comes what the lower energy is for sigma 2pz for oxygen, fluorine and neon. But for boron, carbon and nitrogen, after sigma star 2s, which comes the pi 2px and pi 2py. After that only the sigma 2pz is coming. So only here the change is there. Other than this, the antibonding is similar in both the cases. While drawing the molecular orbital diagram, you have to keep in mind and then how to fill the electrons. It should be filled according to the laws, that is Aufbau, which is obeying the Pauli-Jean exclusion Hund's rule. That is lower energies are filled first and then only the higher energy is filled. So in this the bonding will be filled first, after that antibonding, then again the bonding, antibonding. Like this the filling is there in the molecular orbital. And here the molecular orbital diagrams I have given in the Google Classroom. So you can go through the diagram. For up to neon you have to learn. So go through that one and learn from the file. Now let's see the stability of the molecules. If we consider the Nd as the number of electrons in the bonding molecular orbital and Na as the number of electrons in the anti-bonding molecular orbital, then the molecule is stable if Nb is greater than Na, and the molecule is unstable if Nb is less than Na. That is, in the first case, more bonding orbitals are occupied. In the first case, the number of electrons will be more in the bonding molecular orbital, and so the bonding influence is more. And that's why the molecule becomes stable. While in the second case, the anti-bonding influence is stronger. That means there the number of electron will be more and therefore the molecule will be unstable. So these are the cases how we can understand whether the molecule is stable or unstable. Now let's see the next topic, that is bond order. It is defined as one half the difference between the number of electrons present in the bonding and the antibonding molecular orbitals. That is, if we have to write an expression, we can write it as BO or bond order is equal to half into NB minus NA, when NB and Na are the number of electrons in bonding molecular orbital and antibonding molecular orbital. And one more thing we have to notice, that if a positive bond order we are getting, that means NB is greater than Na, and that means what? It is a stable molecule. While if we are getting a bond order negative or 0, negative if it is coming, it will be Nb less than Na. And if it is 0, that means Nb is equal to Na. Number of electron will be equal. And that means the bond order is unstable. Now let's see the bonding in some of the homonuclear diatomic molecules. First case, we can take the hydrogen molecule, and it is formed by the combination of two hydrogen atoms. Each hydrogen atom will be having one electron in its 1s orbital. Therefore, in all, there are two electrons in hydrogen molecule which are present in which orbital when we combine? When we combine, we'll get that two electrons in sigma 1s molecular orbital or bonding molecular orbital. So the electronic configuration of hydrogen molecule can be written as H2 is equal to, how we can write, sigma 1s2. That means two electrons are in the bonding molecular. And from here we can find out the bond order also. That is, bond order is equal to how? Nb minus Na by 2. The number of electrons in the bonding molecular orbital. That is 2 here. What about the antibonding? Nothing is there. So it is 2 minus 0 by 2, which is equal to 1. That means the two hydrogen atoms are bonded together by a single covalent bond. Next, we can see in the case of helium molecule, Ha2. The configuration when we write, we will get 1s2. And each helium atom consists of 2 electrons. So, how we can write He2 molecule will be having 4 electrons altogether, right? And these electrons will be accommodated in which all orbitals? Sigma 1s and sigma star 1s molecular orbital. So how we can write the electronic configuration? That is sigma 1s2 sigma star 1s2. And after finishing this electronic configuration, we can get the bond order of helium 2 molecule, and it can be written as what? 2 in the bonding minus 2 in the anti-bonding molecular orbital divided by 2. You will get what? 0. That means this molecule is unstable and it does not exist. Similarly, we can see for beryllium 2 molecule also. It is 1s sigma 1s2 sigma star 1s2 sigma 2s2 sigma star 2s2. And here also we know that how many electrons are there? 4 minus 4 by 2. You'll get what? 0. That means this molecule also does not exist. Like this, we can find out that whether the molecule exists or not. Now let's see the different types of hydrogen bonds. There are two types. They are intermolecular hydrogen bonding and the other one intramolecular hydrogen bonding. First, we will see the intermolecular hydrogen bonding. It is formed between the two different molecules of the same or different compound. And we can give the example as in HF molecule, alcohol or water molecules, the hydrogen bonding is of intermolecular hydrogen bond. We can see in the diagram how the link is there between the hydrogen and oxygen in the water case, and for fluorine and hydrogen in the case of HF molecules. So this is said to be intermolecular hydrogen bonding. And when we take intramolecular hydrogen bonding, it is formed when the hydrogen atom is in between the two highly electronegative element or atom which is present within the same molecule. That means the same molecule is having the hydrogen and it is situated between the two electronegative atom. Then we can have a hydrogen bonding between the electronegative atom and hydrogen. So that what happens? There forms the intramolecular hydrogen bonding. An example is given with orthonitrophenol, and the hydrogen is in between the two oxygen atoms here. In this, we can see that a benzene ring is there where the functional group OH is there, and in the adjacent position a nitro group is there. And in this we can see the hydrogen bond can be formed between this oxygen and this hydrogen. Here the oxygen is getting a negative charge and hydrogen is getting a partial positive charge, and these two things are in the same molecule. So it is said to be intramolecular hydrogen bonding. So this is about the different types of hydrogen bonding. With this we are concluding our chapter. Thank you. We'll see you in the next session.